All right, so for this, you needed a periodic table. It helps if you have a periodic table to look at. On the test, you will be given a periodic table to use. It won't have any colors on it. It'll just have the element names and symbols, the atomic number, and the average atomic mass. So it will have that information included on it. So the location on the periodic table, in general, the metals are on the left side. In general, gases are on the right side. Number 3, in general, good conductors are on the left side because they're the metals. In general, poor or non-conductors are found on the right side because remember, that's a property of non-metals. Where can you find the metalloids? They are on that stair step. Okay, starting with boron and going down to astatine. All elements in the same group have the same number of valence electrons. So remember, our valence electrons are the electrons on the outermost energy level. And so in the same column, remember we call the columns groups or families, they have the same number of valence electrons. The rows are called periods, so all elements in the same period have the same number of energy levels. So remember, in our Bohr-Rutherford diagram, it shows the whole atom. It shows the nucleus, it shows the protons and neutrons, it shows all the electrons. And so our first energy level can hold a maximum of 2 electrons. The second energy level can hold 8. The third energy level can hold 18, but remember that 8 is kind of our magic number. So it fills up with 8, and then it actually jumps to the next energy level before it falls back. And the fourth energy level is 18 or 32, I think. But 8's our magic number. It holds a lot more. Yes?
What do you mean by like the magic number?
That atoms are most stable when they have 8 electrons in their outer rings, with the exception of the first energy level. So they call that a stable octet. So our noble gases, with the exception of helium, all of the noble gases have 8 electrons in their highest energy level. Okay, so that's kind of like a magic number. It makes the atom very stable. Okay. So you need to be able to label your groups here. Right, so group 1 are the alkali metals. Group 2 are the alkaline earth metals. Groups 3 through 12 are the transition metals. Group 17 are the halogens. Group 18 are the noble gases. The cluster along the stair step are the metalloids. And the 2 rows below the table are sometimes called the rare earth metals. Sometimes they're called the inner transition metals. Sometimes we call them the lanthanide and actinide series. Okay, so what element is located in group 10, so the 10th column, and period 4? So you should have put nickel. Which element is located in group 14, period 3, you should have found silicon. What element is located in group 2, period 6? I should have had barium, Ba. Valence electrons are electrons in the highest energy level. Okay, so the outermost or the highest energy level, farthest away from the nucleus. So Lewis dot diagrams have dots that represent the valence electrons. So remember, the Bohr-Rutherford diagram shows us all of the electrons, but the Lewis dot diagrams just show us the valence electrons. There should never be more than 8. That's the maximum number. And they determine our chemical properties. Any questions about those? Okay, good. All right, so remember we did an activity where we colored a periodic table, and we said that we can determine how many valence electrons there are in atoms based on the column that they're in, or the group. So group 1 has 1 valence electron, 2 has 2, and then remember we said that in the modern way of labeling the column, 3 valence electrons come in column 13. The old school way was to label it 3, Roman numeral 3A. Okay, and that kind of, if you have that kind of labeling on your periodic table, that can sometimes be a little bit of a help because the Roman numeral tells you the number of valence electrons. But 4 valence electrons are in group 14. Any questions about that? All right. So, elements with 1, 2, or 3 valence electrons want to lose electrons, and they will become positively charged, and we call that a cation. Okay? So if they have less than 4 valence electrons, they want to lose all of their electrons, all the valence electrons, and they become positively charged. Elements with 5, 6, or 7 valence electrons want to gain more. They want to gain so that they have 8, and they will become negatively charged. And we call them anions. Any questions about that? We're good? Okay. Elements with 8 valence electrons are stable. We say that's a full octet or a complete octet. And they do not form ions or compounds. Remember, those are our noble gases. So 25 says, if an element has 3 valence electrons and 3 energy levels, what group is it in? So the group has to do with the energy level. The group has to do with the column. So which column has 3 valence electrons that we just filled in up above? 13, yeah. Okay. The period is the number of energy levels. So there's 3 energy levels. So we want to find the element that is in group 13, and the third column is going to be aluminum. Okay. So an element has 6 valence electrons. That means it's in column 16. And it's in the 4th period because there's 4 energy levels. And so the element is selenium. So if an element has 2 valence electrons, it's in the 2nd group and the 5th period. And so 2, 3, 4, 5, it's strontium. So far, so good? Okay. If an element has 2 valence electrons and 3 energy levels, it's going to be in group 2. It's going to be in the 3rd period. And its symbol is going to be magnesium. So 5 valence electrons, that means it's going to be in column 15. Period 5, because it has 5 energy levels. So 1, 2, 3, 4, 5. And group 15, go over. This is going to be SB, antimony. Are we doing okay? All right. Slide down here. So, if an element has 7 valence electrons and 2 energy levels, it's going to be in group 17. Period 2, and so that means that it's going to be fluorine. All right, so 31 says, name 2 elements that will be the most similar as far as chemical properties to chlorine. So what we want to do is we want to find chlorine on the periodic table, and we want to find the element that's directly above and directly below. Those are the ones that have most in common. Remember, the columns are called groups or families. So there's a family resemblance between the elements in the same column. So fluorine and bromine are going to be the most similar to chlorine. Okay, so chlorine's atomic number is 17. Remember, that's the whole number on the periodic table. That means that it has 17 protons. And if it's neutral, it has 17 electrons. And so the energy configuration, or the electron configuration, we're just going to list how many electrons are on each energy level. Remember, the maximum numbers that we can have are 2, 8, 18, 32, okay? So this has 17 electrons, so there's going to be 2 on my first energy level, 8 on my second, and 7 on the third. None on the fourth. So remember, the valence electrons are the ones on the last or the outermost energy level, and so this has 7 valence electrons. It is in column or group 17. And chlorine is in the 3rd period. Its Lewis dot diagram is going to look like this. It's going to have chlorine and then 7 dots around it. Remember, it's just the valence electrons. So remember, elements with 1, 2, or 3 valence electrons want to lose their valence electrons. 7, 6, or 5, they want to gain. So they want to gain, and it wants to gain only 1 because it wants to get to that magic number 8. Okay? So if we stop and think about it here, the neutral atom has 17 protons and 17 electrons. The charge on 17 protons is positive 17, and the charge on 17 electrons is negative 17, right? And so when we add those up, we get 0. That's a neutral charge. If this atom gains an electron, we're going to change our number of electrons here. So we're changing it to 18. So 18 electrons. That's going to have a negative 18 charge. And so the overall charge for my atom is going to be, or for my ion, is going to be negative 1. I have 1 more electron than I do protons. And my average atomic mass is the decimal number on the periodic table. So that's 35.45. And the units are AMUs, atomic mass units. Any questions about those? All right. Okay, so the number of neutrons when the mass number is 36. So remember, our mass number is just the total number of protons and neutrons. So mass number equals the number of protons plus the number of neutrons. All right, so if my mass number is 36, and I have 17 protons, then I want to know how many neutrons do I have. And if I solve that, I'm going to get 9, right? No, 19. Can't add. Okay. What's the mass number when the number of neutrons is 20? So remember, my mass number is protons plus neutrons. So my protons, this is chlorine, so it's 17. And my neutrons are 20. And so my mass number is going to be 37. Any questions? I'm doing okay. All right. So let's see. For number 33, it says complete the chart. So the first one, they just give us our atomic number, our neutrons, and our electrons. So our atomic number is 6. So we're going to look at our periodic table and find atomic number 6. And that happens to be carbon. Okay. Because its atomic number is 6, that means the number of protons is 6. And the mass number is the protons plus the neutrons, so that's 14. there are 6 electrons, so this is a neutral atom. And so this is how we write the shorthand. We're going to write the symbol for carbon. We're going to put the mass number up here to the left and the atomic number on the bottom. Okay, so sometimes we call that isotope notation. Okay, so this next one, they give us the shorthand here. So this is giving us a lot of information. It's telling us by the symbol that this is barium. It's telling me that my mass number is 56. I'm sorry, my mass number, my atomic number is 56. That's this number down here. That's the number of protons in the nucleus, right? The mass number is 140. So to find the number of neutrons here, we're going to take 140 minus 56. We get 74, is that right? Am I doing my math right? No. 84? Yeah. So 84 neutrons. Now the charge is +2. That means it has 2 more protons than it does electrons. So since I've got 56 protons, I'm only going to have 54 electrons. That's how it gets it a +2 charge. All right, so phosphorus. We're going to look up phosphorus on our periodic table. It's atomic number 15. That means it's got 15 protons. My mass number is 32. And so to find my neutrons, I'm going to take 32 minus 15. So I get 17. I've got 18 electrons and 15 protons. And remember, my charge equals the number of protons minus the number of electrons, okay? So my charge is going to be -3. So for my shorthand here, I'm going to write phosphorus. I'm going to write P -3. And then my mass number is going to go up on the top. So this is going to be 32. And my atomic number is going to go on the bottom. And that's going to be 15. Okay, so complete the chart. So we have to know where the subatomic particles are and what their charges are, what their masses are. So the protons and neutrons, remember, are in the nucleus. And the electron is in the electron cloud, sort of swirling around the nucleus. The relative masses, so protons and neutrons are about the same mass. They're very, very close. And electrons are approximately 0 AMUs. It's not quite 0. It's pretty small, though. The charge, protons have a +1 charge. Neutrons have 0 charge, and electrons have a -1 charge. Okay. So the role in the atom, protons determine what element it is. So it determines the identity. So if we change the number of protons, we change what element it is. Neutrons stabilize our nucleus and keep it from flying apart. Okay? And the electrons determine the chemical and physical properties. Okay. Okay. All right. So, oxygen 16 and oxygen 18 can be described as isotopes. So the word is isotopes. This means they have the same number of protons and a different number of neutrons. So they have different masses. So an ion is a charged particle So an ion of an element has the same number of protons, but a different number of electrons. Okay? So to form an isotope, what's changing are the neutrons. To form an ion, what's changing are the electrons. So draw the Bohr model for a neutral atom of phosphorus. So phosphorus has an atomic number of 15. It doesn't tell us how many neutrons, so we're just going to put the protons in our nucleus here. And so we're going to draw these on here. There's 2 on my first energy level, and then there's 8 on my second energy level. Remember, that's the maximum that it can hold. And then there's 1, 2, 3, 4, 5 on my third energy level. So it has 5 valence electrons, and my Lewis dot diagram for phosphorus looks like this. Got 5 dots around it. So the word we're looking for here is intermolecular, not inter, intramolecular can't spell. I was right the first time. Intermolecular forces are the interactions between molecules and particles, and it's a measure of how strongly the particles stick together. So stronger intermolecular forces cause substances to have higher melting and boiling points. So the higher the melting or boiling point, the stronger these intermolecular forces are that are holding them together. All right, so the father of the modern periodic table was Dmitry Mendeleev. He was Russian. And he organized the elements in order of increasing atomic mass. Now, that's not how our periodic table is arranged, but that was how he arranged his periodic table. Now we arrange our periodic table according to increasing atomic number. So the number of protons in the nucleus. Okay, they didn't know about protons, neutrons, and electrons back when Mendeleev was making his periodic table. So the 2 most reactive groups on the periodic table are the alkali metals and the halogens. Groups 1 and 17. The reason why they are so reactive is because they only need to gain or lose. I should say lose or gain. One electron to become stable. Okay, so the alkali metals just have to lose one electron and they're stable. They have a noble gas electron arrangement. The halogens just have to gain one electron to become more stable. All right, so predict the combining capacity for the following given these formulas. So they're giving us these formulas, MgO, Na2S, and Al2N3. So we're just going to do a little research on our periodic table to see what columns these are in. So magnesium is in column 2. Oxygen is in column 16. Sodium, Na, is in column 1. Sulfur is in column 16. Aluminum is in column 13. And nitrogen is in column 15. So, to figure out what the formula is going to be for calcium and sulfur, we want to see what columns those two elements are in. So, calcium is in column 2, and sulfur is in column 16. And so, because it's in the same, they're in the same columns as for magnesium oxide, the formula is going to be the same. It's going to be 1 to 1. So, the formula for calcium and sulfur is going to be CaS. Just like magnesium oxide, because elements from the same two columns combine in the same way. Gallium is in column 13, and phosphorus is in column 15. So since these are in the same two columns as aluminum and nitrogen, when they form a compound, it's going to be Ga2, P3. And our last one, potassium is in column 1, oxygen is in column 16, and so these are going to combine the same way as sodium and oxygen. So this is going to be K2O. Does that make sense? All right. And our last question here. So it says, given the boiling points for, that's the last one, isn't it? Okay. Given the boiling points for chlorine and iodine, predict the boiling point for bromine. So in our periodic table, the halogens go fluorine, chlorine, bromine, and iodine. Okay? And they're telling us, these two, they're telling us chlorine and they're telling us iodine. And they want us to estimate bromine, okay, which falls right between those two. And so to find the estimate, what we're going to do is add those two boiling points together and then divide by 2. Okay? So we're going to take I'm going to add those two together and we get 153.4 degrees Celsius, and then we're going to divide that by 2. So we get 76.68. Okay, so we know that the boiling point for chlorine is negative 34.04. And we've just figured out the boiling point for bromine is 76.68 degrees Celsius. And iodine has a boiling point of 187.4 degrees Celsius. And so the question is, would you expect fluorine up here to have a higher or lower boiling point than chlorine? So it's going to be lower, right? Because it's increasing as we go down the column. Okay, so intermolecular forces, higher boiling point, stronger forces. So that means we're going to have to go fluorine, chlorine, bromine, iodine. Okay, so the trend for atomic radius, remember they get smaller as we go from left to right. They get bigger as we go from top to bottom. So if I'm looking at tin, antimony, and tellurium, the smallest one is going to be Te because it's farthest right on the periodic table.